Hello everyone! Welcome to this follow-up video to my last video where I created a Pac-Man clone from scratch in C. At the end of that video I managed to create a functional game, but it was really quite bare bones and lacked many features. I figured there's still some room left to improve this project, so in this video I'll go over what I added to this clone to go from this to this. The first thing that I did was refactor some parts of the code. I moved most of the OpenGL code out of the Windows platform layer and into the cross-platform portion of the code, for instance. OpenGL still requires some setup that is unique to each platform, but once that's out of the way, the rest of it is actually cross-platform. Once that was done, I wanted the game to have levels that were of any size, because at this point I only ever had a single level that was hard-coded in a static array. So in order to have levels of any size, it would make sense to start working on scrolling. As a quick recap to how rendering is done in this game, basically it's handled by doing all of it in software and writing pixels out into a frame buffer that lives in system RAM. Once all of the rendering for a frame is done, the frame buffer gets copied over to an OpenGL texture, which is then uploaded to the GPU and drawn on a single textured quad. Alright, with that recap out of the way, let's get back to what I did next. I started out by specifying offsets in the X and Y axis and the scaling factor that could all be passed to the shader. These parameters won't actually allow the type of scrolling that I want with my current setup, but I added them as a way to add some extra flavor to the camera movements later on. When I used the offsets in the pixel shader to get the camera to scroll, it would result in this really trippy effect, and even though it looks kind of cool, it's obviously not the effect that I wanted. The reason why this happens is because the texture is rendered at its full size at all times, and whenever we start scrolling, we see the wrapping effect that is set on the texture. In my case, I had set it to clamp to edge, which results in this trippy looking effect. One possible way to fix this is by supplying the GPU with a bigger texture and making sure that we only see a portion of the texture at all times. What we then need to do is draw the tiles that are just outside of the visible range and in the direction that we're moving towards. We also need to change the wrapping parameter from clamp to edge to repeat for both axes. This approach is actually really similar to how old hardware like the NES or Game Boy handles scrolling. Another possible way to handle scrolling would be to offload all of our drawing operations to the GPU and let the GPU take care of it. But that's obviously not really an option, because I wanted to go with a software-based approach to rendering for this project. Anyway, I went off on a complete tangent there. The way that I ended up implementing scrolling was by simply extending the current drawing functions by keeping track of a camera position. The way it works is that the player is almost always centered on the screen, and what we effectively end up doing is move the entire world around the player, which is done by subtracting the camera position from the level tiles and ghosts. The only time the player is allowed to go off center is whenever we reach a corner of the level. At that point, we stop scrolling and let the player move around in that section of the map. Anyway, after I added scrolling, I wanted to be able to load levels from disk. I figured I would go with comma-separated values, or CSV files, to represent the game level data. This format is exactly as its name implies, which is nice because it's a format that a map editor like Tiled is able to export to, and it's structured in a similar way as the static array that I was using previously. To add support for this, I first removed the hard-coded level and I needed to create a common interface for level data. Once I had that, I also added some utility functions that I could use to retrieve tiles or tile data from. Of course, my rework introduced some bugs and it gave me some weird results. Turns out, I made a mistake by accidentally swapping the rows and columns around in the utility functions. So after fixing that error, I now had a new error. This time it was an out of bounds access issue whenever I would try to wrap around the level. Once I had that fixed, I of course introduced another issue, because now the player could end up outside of the level. So yeah, this is the process of programming in a nutshell. Once the major issues had been dealt with, I moved on to adding support for loading levels from disk. I started out by moving the hard-coded array that I previously used for the level out into a file that I could then parse, load, and feed to the game state. As expected, this change also introduced some new issues and a crash. However, the fix turned out to be incredibly simple, because what I forgot to do was to add the space character as a delimiter in the file loading function. So now that I was able to load my levels from disk, I somehow introduced a bug where pellets past a certain X value were no longer being eaten by Pac-Man. This was again because I swapped the rows and columns around when parsing the level data. I'm not sure why I kept making that same mistake for some reason. I also wanted to replace the game's graphics and go with a 1-bit art style. However, I was starting to regret my decision to initially go with sprites that were 16 by 16 pixels in size, because I found it tricky to create something that looked better than what I already had within those constraints. Because of this, I decided to instead go with 32 by 32 pixels for the new sprites. But before I started working on the new tile set, I first upscaled the existing one to those dimensions and made sure that was working before creating the new tile set. After I updated the game to make use of the larger sprites, the game appeared more zoomed in, of course. This was pretty interesting because it directly affected the visibility and gameplay. So from a game design point of view, I wasn't sure if I wanted to keep it this way or to fix it so that it would look like it previously did. I decided to not make the decision at this point and to get back to this later on because I was still a bit indecisive, but I'll spoil it anyway. I ended up leaving it zoomed in, not because I had a really strong game design reason, but simply because I got used to it by the end of the process, which is a terrible reason, and it's something that I've seen being brought up a lot in the game design circles. Because as the person making the game, you get so used to what you're creating that it's often easy to overlook the fact that it might not translate that well to other people who are going to be playing your game. Anyway, enough about game design. Let's get back to what we focus on in these videos, which is the programming part of game development. Another feature that I wanted to have was the ability to apply affine transformations to sprites, namely scaling and rotating. To get started with this, I had to first add a couple of common math functions, such as a way of multiplying matrices together and also a way to multiply a matrix by a vector. The first type of transforms that I focused on were rotations, and the initial results were not exactly what I was looking for, but they were exactly as I expected them to be. Without any modifications to the code, any transformation that I applied to a sprite would always transform it relative to the top left corner of the sprite. There was another problem that came up, as you can see, because now I had these weird holes between some pixels, but I'll get back to that in a bit. So the way to fix the anchor point issue is to first translate or move the sprite over by half of its width and half of its height. This way the center of the sprite aligns with the origin. Then the transformation should be applied, in my case a rotation, and finally it needs to be translated back to its initial position. Anyway, once I made sure that the rotation was happening about the center of the sprite, I had to address the holes that appeared between some pixels. These holes between the pixels are a result of the method that I was using, which is called forward mapping. This is a method where we start from the source sprite and traverse and transform every pixel based on the transformation that we supply to it. The reason why the holes start appearing is because this method only works on the pixel that our source sprite actually has. So when you scale up, for instance, these artifacts show up because we simply don't have the pixels in our source sprite to transform from. This can be fixed by using another method that is called inverse mapping, which is essentially the opposite of forward mapping. So how does that fix the issue? What we do in inverse mapping is we first determine where the transformed sprite will end up on the screen, then we apply the inverse transform on every pixel of that destination to transform back to a pixel on the source sprite essentially. This means that certain destination pixels will most likely end up sampling the same source pixels, and that prevents the holes from showing up. But before I could change my code to use inverse mapping, I first had to actually create a matrix inversion function. I was using 3x3 matrices for this project, and inverting a 3x3 matrix isn't too difficult, but it's very error prone. So I did it step by step and I wrote it out on paper first. I took it really slow and made sure the code matched up with what I had worked out on paper. Once I had the implementation done, I wrote a test to see if the results were correct. I compared my results to what I had worked out on paper and against a couple of online calculators, and I was shocked to see that I had actually implemented it correctly in one go. I'm so used to things not fully working the first time around, so on the rare occasion that it does happen, I feel like it needs to be mentioned. The next thing that I wanted to add were spotlights to the characters and power palettes. I started working on creating a drawing function that did just that, and I avoided creating a generic circle drawing function. Getting the spotlight effect is achieved by creating a radial gradient, so that's something that's baked right into this function. I went with a pretty straightforward way of drawing a circle, but my initial implementation of the gradient led to me drawing Pac-Man on top of Pac-Man. One thing that wasn't sitting well with me with this implementation was the fact that I was computing a square root for every single pixel of the circle to get the gradient. It wasn't until after I was done with everything that I realized that I could simply use the squared distance instead. So I did end up making this change, but it wasn't until the very end. Even though I was able to draw a radial gradient at this point, the falloff that's created by the gradient was never meant to be rendered like this. Instead, I wanted to draw the falloff in a dithered style that I think matches better with the 1-bit art style. So the values produced should be thought of more like a weight that is used to determine the density of the dithering. I also played around with adding a resizable radius, which I liked because it made it look slightly more alive. One problem with my approach to spotlights was that they wouldn't blend if multiple spotlights were drawn close to each other. This happened because whenever a new spotlight was added, it would simply write its values to the frame buffer without taking any existing values into account. To fix this problem, I created a separate buffer that I would use to accumulate and clamp all of my light values to. That buffer would be used at the end of the rendering function to create the final result by multiplying each pixel in the frame buffer against each pixel in the light buffer. Around this point, I switched out my texture atlas for the 1-bit styled atlas that I had prepared on the side. I also decided to finally do something about all of that moonwalking that Pac-Man did, and I made use of the affine transforms that were in place now to fix that issue. The next thing that I added was a text drawing function, and with that in place, I could visualize the score and lives count, which helped in making it resemble an actual game slightly more. At this point, I also added a way of loading the next level whenever the current level's palettes were fully cleared. I did this by using the loading from disk function that I created before, but I had never actually used it before, so I discovered a problem with it. I was using two Win32 functions, which are called findFirstFile and findNextFile, and I was assuming that I would always get the files in alphabetical order. I had never actually used these functions before, and it turns out that there is no such guarantee. From what I understood is that it returns the files in the order that they show up in the underlying file system, and not how they appear in the Windows Explorer. Anyway, I fixed this by parsing all of the names up front and sorting them in alphabetical order. Whenever a new level is loaded, it simply does a lookup and fetches the next file name that it will then attempt to load. I implemented this in the most basic way using the standard C library's string compare function, which also has its own problems when it comes to things like leading zeros, but I didn't bother dealing with the edge cases if I'm being entirely honest. So there's still some ways to trick the game into messing up the ordering of the levels, but it was good enough for this project, so I left it as is. As I was beginning to near the end, I did some final touch-ups and small additions before wrapping it up. I added a little get ready message at the start of every level. I also added a mandatory screen shake whenever a pellet or ghost would be eaten, and I added a menu as well to pause, continue, or quit the game. The last two things that I did was port the game over to Linux, and I used X11 to handle window and OpenGL context creation. This was actually the first time that I had done this directly using X11, because I normally just use SDL on Linux, but I wanted to stay in the spirit of writing everything from scratch that I started this project out with. It wasn't very difficult, but it did involve some investigation and experimentation until it worked. The other thing that I also added were some SSE intrinsics in a few places in the rendering code to process some stuff simultaneously, but I didn't go too overboard with this. Having said that, the rendering functions really lend themselves well to using SIMD and multiple threads. The same goes for the matrix multiplication functions, which could really be sped up by using these intrinsics. So those are interesting areas to explore in order to improve performance. However, I didn't find it really necessary to do so in the end, because when I ran the final version of the game as an optimized build, I would hit around 800 to 900 frames per second when VSync was turned off, so that was fast enough in my opinion. Anyway, those were all of the things that I added to the Pac-Man clone. I had a lot of fun adding these things and polishing the game up a bit. Of course, it could always be expanded upon even more, but I feel like it's pretty decent now, and I'm planning on working on some new projects next that I'll be sharing with you in my upcoming videos. Thank you for watching, and I hope you enjoyed this video. Take care.